Well, let me introduce myself. My name is Santiago Yepez. I am professor at the University of Concepcion in Chile. I am a specialist in hydrosedimentology and remote sensing. And currently, I am the regional coordinator of the FRIEND-Water Lab Amigo in this moment. FRIEND-Water, as you know, this is an international network of experts that is supported by the Intergovernmental Hydrological Program. And this program studies long-term changes in river discharge to better understand how natural processes and human activities affect the availability and distribution of water across time and space. Well, in this moment, we have three main resource line that is focused in three modules. The first is river system and hydrogeomorphology. We try to apply the framework like river style, um, different techniques in remote sensing and GIS technique in order to apply these techniques in the river restoration and some approach to assess the human impact. We also evaluate the landscape evolution and feedback. We evaluate the tectonic, erosion, and geochemical modeling in order to understand the evolution of the basin and also to understand the sediment transport. We touch some topics like groundwater contamination, how we going to show today with the talk of Jose Margotta. And also we evaluate the land use impact and how this influence the evolution of the basins. And in the other side, we have specialists working in climate change and water resource. The idea is try to understand the rainfall patterns, water security, and so process like El Nino, and try to understand this process and the problems related to, for example, flow risk. And also it's very important for us to understand the ambient data gaps and how we can use this information to the management adaptation in a context of climate change. The idea is to obtain a holistic understanding of hydrological and geomorphological process in order to apply science-based strategies for conservation and also for the rivers management. Well, some of the activities that we develop currently in the FRIEND-Water Lab Amigo is related to the different seminar and workshop. And in this case, we have the collaboration with the different institutions, for example, the World Meteorological Organization with that, and also the Tela Instituto. And the idea is try to create different seminars, several seminars related to the practice experience in hydroacoustic techniques. We recently organized 4 seminar workshop. We talk about the effect Doppler and how to use equipment like ADCP to study the water discharge. And also we share the best practice using this kind of equipment, and also how to combine the signal of the backcasting from the ADCP and also combine with the different suspended sediment data at different depths in order to create inversion models to estimate the sediment transport in the water column of the large rivers. Well, we developed different workshops and in July 2024, in August and September, and also the last was in October. We combined also this technique with some research related to the new satellite swap in order to evaluate the water level in lakes and also in the rivers. We have the support of some collaboration in Argentina. We show some new software in order to quantify the suspended sediment concentration, applying a different approach using ADCP equipment. Well, my presentation is very short. I'm going to show the main activities that we are carrying out and the future events. We develop this workshop. We are we expect to have the first draft UNESCO book focus in the risk prevention and fluvial hydromorphological hazards on the climate change. We have the collaboration with different partners in Latin America and the Caribbean, Europe, and USA. We planning to submit an evaluation, a new project to study the sediment transport using high spectral techniques and morphodynamic approach in order to understand the sediment transport in the Rio Biobío here in Chile. And we assisted to the EU General Assembly in 2025 in order to present the last works in water quality in 4 lakes in the south of Chile using hyperspectral techniques and also time series of satellite images in order to understand the eutrophication process in these water bodies. I would like to show some presentation of the UNESCO book. It's in preparation, but the idea is talk about different topics that we are in working today in different parts of the Latin American and Caribbean in the framework of the FRIEND-Water. We call this new book, Fluvial Hydromorphological Risk Prevention Under Climate Change, and we take some different topics like, for example, the fluvial risk, the characterization of river across the geomorphological approach, as the river style, using geomorphic assessment in order to predict the evolution of the river. We talk about hydraulic modeling, building future climate time series at monthly and daily, and also damage and loss estimation. And I'm not sure if he is the last topic will be developed, but we are planning to talk about nature-based solution and for fluvial risk reduction also. And my presentation is very short. I want to now to give the word to my partner Jose Margotta. He is expert in sedimentology and also depositional environments. He going to talk about the groundwater contamination, and he is expert in remediation projects in order to understand the groundwater contamination in Patagonian south.
Well, as mentioned, Santiago, I'm currently working here in Chile, applying some remediations for soils and groundwaters. Actually, I'm working. I'm geologist working for GB5 or GB5 environmental consulting company here in Santiago, in the Chile and all the country, the whole country, and also as an associate professor at the University's Andrés Bello, almost for environmental geology and energy resources, energy resources. So just to start, we are going to talk about we know that the Patagonia is an area that is having a lot of interest in terms of critical resources. Globally, is a region which is very important. Also, is a gateway for crossing the ships between Atlantic and Pacific Oceans. Also, is having a lot of trouble during this context of climate change. So, first of all, we are going to briefly speak about the soil characteristics that we have in the region, in the southernmost part of Chile is Magallanes region, the importance of remediation for this area, some challenges that we are having during our studies, some of the remediation techniques that we use for soil and water in Patagonian area. The examples or the images that I'm going to put here are real cases of our study, and then some of the next steps and conclusion of this presentation. It's important that we understand that these all the remediation techniques are aligned for the sustainable development goal of the world. Actually, we have two main development goals that we are linked directly to when we are speaking about remediations and treatment of soils and groundwater. One of these one is about life and land. We know that the UN is working through different projects and UNESCO as well, trying to protect and restore different ecosystems, try to combat the degradation of the soils, and reverse all the biodiversity lost. And also, we need to understand that we are living in a context of climate change that is having a lot of impact in the world. So the effects are already visible, and we're seeing always catastrophic actions in different parts of the world. So this change can provide huge opportunities to improve the infrastructures and also the different techniques that we use to create some reuse or improvement of the soils and the groundwater in our different regions. For the southernmost part of Chile, which is the Magallanes region, is this one that is actually the last part of the continent as well. We are going to be focused in Punta Arenas, which is the bigger city of the region, like the capital of this region, which is a coastal city, and it's just close to the Strait of Magallanes, and is having it's a unique city because it's not only because it's really beautiful, it's because it's having several environmental conditions, a subantarctic environment. Also, is unique because it's high winds, precipitations, and it's having a huge cultural value for the country. So all the processes that can destroy these or degrade these soils and the groundwater of this area is impacting directly in not only the environment itself, is not all the key economic trends that we have in the city and in the region. This is an area in the southernmost part of the continent that is having not only high winds, it's highly annually, is having a lot of precipitations, almost 1,000 millimeters per year. So it's one of the areas which high precipitation in the world is. This is having, or this is creating a lot of infiltration and lixiviation of the different contaminations that we can obtain for the industrial activities. Passing through the soil characteristics that we have in this area, the soils are, or the geomorphology and the geology of the area is really shaped by the quaternary glaciation. We have this post-glacial processes and volcanism. Really, the evidence of these ones are really important in the area. We have mountain with very low altitude, not that 1,000 meters above sea level. The valleys of the quaternary area are really linked to fluvial and lacustrine deposits. Some of the characteristics that we can see when we are doing some environmental works is that is having a lot of it's highly heterogeneous. The soils are highly heterogeneous. The deposits have even if we have some, we can see here, for example, in this part, that we have some lacustrine deposits, evidence of the lacustrine deposits. Mainly the whole area is having very low organic matter and is really sensitive to disturbance. All the soils is very sensitive. So when you can see during the drilling of usually the sediments are having sand-sized particles. You have a lot of pumice fragments. You have widely distributed in the soil, which you have several evidence of igneous and metamorphic rocks within the sediments. So you have a very heterogeneous material with thin material or ash for the volcanism. So it's a soil that is really influenced by the evolution, or mainly the climate evolution of the region. Also, the other part that is very important is that you have the cold climate is really influence all the characteristics that you have in the region. Different type of formation, alluvial terraces, moraines, colluvial deposits, are really developed in the soils in the area. Sorry. All the properties are really unique for this region. It's for that applying some techniques, even if or for remediation of these areas, even if you have the techniques that you can apply in another part, applying in this area of the continent is having some special applications. And why is important the remediation for this area? Actually, the continent or the Patagonian soil is having a lot of soil degradation. In this moment, you have not only spills or oil spills, you have deforestation, heavy mineral or heavy metals for mining are reducing a lot of soil fertility. So the importance of maintain these areas are really important not for the region. It's not to avoid all the degradation processes of the natural system that you have in this part. The groundwater is vulnerable. You have some shallow, mostly of the phreatic levels and the unconfined aquifer are really shallow. So it is they are having also a lot of issues, a lot of issues for to degrade the spills and also the infiltration of the contaminants and the volatilization due to this cold climate as well. And the other thing, the other part that is important is the ecosystem. You have a lot of issues as well trying to for carbon sequestration of the global temperatures, the biodiversity and the role that is having this region due to the contamination that you can that are increasing in this area. Also, you have some difficulties in Magallanes region due to the oil spills. Due to this part in which you have this transit of ships, important because it's the last big city before changing between Pacific and Atlantic Ocean, and you have a lot of commercial activities between Argentina and Chile as well for that area. So it's having a lot of is providing a lot of issues, not only for tourism, it's not also for local fisheries. King crabs, salmon fish are vital for Punta Arenas economy and for the region as well. So when you have these critical parts, you cannot slow the natural degradation processes. You need to try to new techniques that decrease the persistence of the contaminants in water and sediments. Actually, the problem when you have this kind of contamination is the renewal of the juvenile fishes or the juvenile ecosystems. So cold temperatures cannot help this natural biodegradation. So the processes of leading new population renewal are really complicated. So for that the remediation of the soils and avoid degradations of the soils and groundwater are really important. Well, we have four challenge or important challenge to when you are in remediations here. One of them is the cold climate. Low temperature slow the microbial activities, limiting some of the natural or the most sustainable remediations. Then the soils activity that I already mentioned, the heterogeneity of the soil, also the proximity to the strait due to the risk of runoff into marine ecosystem of these contaminations, and also the remote location due to the distance of Punta Arenas and the Magallanes region. Compared with the other big cities of the countries, we have limited infrastructure and the cost and access are sometimes complicated. So it's for that try to generate remediation strategies in this area, need to always take in consideration this part. Then you also we mentioned several times cold climates, so and it's maybe the main point to reduce the effectiveness of natural degradation. Usually, the activity during cold climates is reducing a lot. Every 10 degrees, more or less, the degradation is each time slower. So that means that the timelines increase and also the bioavailability to when you apply your techniques there is more complicated. So then also the significance of the application of the techniques here need to take in consideration which are the type of soil that are altered, or also the properties of the water in terms of the quality that they having. Then the decrease of volatilization, because that depends of the vapor pressure that you have on the soil. So that is also decreasing with cold climate. And then the kinetics of the chemical reactions también are slower during this time. So produce techniques here need to take always that the cold climates always reduce the quantity of or the effectiveness of the processes in this part. So the three techniques that we use to work here in Patagonian areas are pump and treat, biosurfactant, bioremediation, and oxidation in situ. These are some of the pumps that we use for groundwaters. Usually, this is mostly used to manage contaminations, migrations, and also try to remove the mass of the contaminants. Also, biosurfactants that are linked directly to bioremediation because the application of these enzymes or microbes helps to the native microorganisms to break down the large contaminants chains and then generate smaller molecules. And also, it's oxidation in situ. Mostly of it is trying to crystal of a strong oxidant, usually to dilute in water and be applied in the subsurface with the object or the main object is to degrade the contaminant into less harmful chemical species. Here we have some of the techniques that we are working. This is a schematic view of pump and treat remediation. With this kind of methodology you use to control the groundwater and migration, reducing the contaminant flux from the source area, generating the mobilization of the contaminant just to the point of hydraulic control. For this, you generate or put some wells by drilling with environmental techniques. Then you use pumps. This is a view of the contaminants in the groundwater. Actually, this is when you have oil spills and you have this one distributed in the phreatic level, you have the possibility to see the separation between them. And it's for that you, with this one, you start to check and design your methodology and the quantity of well that you need to work. And these are kind of monitoring parts with the PID or the photoionization apparatus. With this one, you can see the gases that you have in your soil. This is a methodology for just to check in laboratory how you are evolving with your quantity of hydrocarbons in the soil during this treatment. Normally, you can see this sometimes huge quantity of oils above the water, above the groundwater, the first unconfined aquifer, and then you start to see when you extract to continue the extraction of the contamination. This is the checking inside the equipment, and then you start to see how it's reducing on time. This is usually, as I mentioned before, the cold climate reduce the treatment efficiency. However, reduce the volatilization and extract the product about the unconfined aquifer is really helping in the control of the contaminant. Then when you use biosurfactants, you try to, usually when you have the infiltration of the biosurfactant, you also generate some wells just to inject the biosurfactant. The biosurfactant is a bioenzymatic treatment where where you stimulate the microorganism in the area using a solution. For that you normally you use a dose to help the viability of the in the groundwater. Usually this is the kind of well that you put in the area. They are 2-inch wells, and depends of the deepest part of the aquifer and the capillary fringe that you have. You start to introduce this manually in the wells, and you check every time this to see and demonstrate the efficacy. Usually this the importance of this is that you enhance actually in cold waters, even they are work effectively, and also reduce more than 90% the emulsification of the hydrocarbons and heavy metals in the area. For ISCO or for the oxidations, you use a strong material, which are crystals of permanganate in this case. This is the oxidation that we use in this part. Try to also, if you see the climate reduce a lot the quantity of or the possibility of biodegradation with this kind of signals. However, the oxidants involved in this area are used in situ and are widespread on the different geological environments. And this is important because the heterogeneity of the soil help you or affect you in terms of the distribution of the other type of techniques. And it's for that they involve in this kind of oxidants that are persist for a long period of time, and the diffusion of them well provide for low permeability materials, help you to fully develop the persistence of the groundwater, and try to avoid treating the charge of to the strait or the nearby fjords. A ver, to see some stories of success, you can see sometimes this is an example of the area of work. You have a complete area where you have the red part are the main points of contaminations. After 1 year of treatment, more or less, the recovery start to decrease with the time. You can see at the beginning a high quantity of liters weekly, and then the recovery start to decrease, and also you can see how it's decreasing on the time. So the evolution showed this is reducing, and then when you start to extract all the contaminants, you can use the biosurfactants into the borders to manage the dilute contaminant that you have in the borders, start to be controlled hydraulically, and obtain the maximum of the free product during a period of time. And then you can use the oxidants in the part that you don't have the free mobile contaminant product, and where the saturations could be irreducible. You try to use the oxidation directly in those areas to decrease at the maximum the contaminant or the concentration of the contaminant in the area. For this area, for the region of Magallanes, it's important the sustainability aspect. The project emphasizes ecosystem-friendly methods. The idea is to generate low impact construction in which the ecological part could be integrated while supporting the the remediation of the area, trying to enhance the energy and limiting the time required. Also, we need to take in consideration that the southernmost part of Chile currently is the emerging of this kind of industry as green hydrogen. Magallanes has the main initiative of this kind of industry in Chile and integrate environmental management strategies and ensure sustainable development of this kind of industry with the community of remediation will be aligning in the same sustainable goals. And then we have a third point, which is minimize the footprint. Actually, the optimized remediations techniques in situ avoid waste, because usually you have previously you had a lot of excavation of these contaminant on soils and transport from this remote location. But now we try to align in situ strategies to implement methods that avoid this transport and waste of energy. Last but not least, for longer time in Chile, we are looking for remediation guidelines. Actually, we don't have a national remediation guidelines, and it's for that we use international standard. But the main focus currently for the country is also generate a guideline with focus on risk-based and ecosystem-friendly methods that can highlight sustainability. Well, so as key conclusions for our studies in Patagonia, first of all, based on the discussions about groundwater in Magallanes, we have that the use of these three techniques has been tailored techniques for this kind of soils with these characteristics of cold climates, highly heterogeneous materials. And we also understand that the remediation, even if they decrease in percentage during normal times, we need to use extended time for with the idea of enhance the natural recovery in situ, and that will be that will help as well the fisheries and discharge into the strait and the nearby fjords, which is marine ecosystems very important that cannot be damaged in Patagonia. Also, we need to understand that sustainable remediations as biosurfactants, they have a high efficacy in this area, more than 90% of emulsifications. These could be very eco-friendly option to enhance hydrocarbon degradation, and also rapidly degrades some of the heavy metals of the minings, and in cold climates cannot increase too much the cost of the remediations. And also, after our studies, we can see that the combination of these techniques help first to contain the hydraulic control of the extraction. Then we can use the dosage of the oxidants and biosurfactant to generate the different chemical reactions that help the increment of the microbial activity and then reduce the impact of the change of the climate. That will be my presentation for today. I would like to thank all my colleagues and also my teammates for the company and also the university to provide me the data to give you this talk, and also all of you for your attention. Thank you very much.
Okay, thanks so much. Good afternoon, everyone. Thanks for sticking with us. I'm going to be talking about the Southern and Eastern African Friend Group with my colleagues listed below. This seminar and presentation is going to focus primarily on Southern African work, with a snapshot into the Eastern African work. And the next seminar that we do will reverse that and have more detail on the Eastern African work. My name is Jane Tanner. I am the regional coordinator for Southern and Eastern Africa based at Rhodes University. I'm also the director of the Arua Centre of Excellence in Water. So in a nutshell, the Southern and Eastern African Friend Group is really tied quite closely to to two different networks. Firstly is the Arua network, which is a network of research-intensive universities over Africa. There are 13 centres of excellence that Arua has awarded in a variety of disciplines, and we hold one of these at Rhodes University. It's the Centre of Excellence in Water. Then the second network that the Friend Group is tied to, the Southern and Eastern African Friend Group is tied to, is a collaboration between Arua and their equivalent in Europe, the Guild. And Arua and the Guild have come together to form 21 Africa-Europe clusters of research excellence. So these are a new collaboration, new clusters. We call them cores. The purpose of Arua is the mandate of Arua is to increase the quantity and quality of African research outputs. The purpose of the core, the clusters of research excellence, are really to strengthen the relationships between researchers on the two continents, and to enhance knowledge exchange in terms of African knowledge and European knowledge and the interchange of this knowledge. So on the left of the screen, I'm just going to give a quick presentation overview because I just jump around a bit just so that everyone can get an idea of where we're going. So I'll go into a little bit more detail about Arua and the core, talk about the main focus area of Southern African Friend, give a snapshot into the Eastern African Friend work, and then our seminar is on a socio-hydrological project that we undertook, but particularly focusing on a participatory allocation modeling tool. So on the right, you see just a little map that we put together showing the different networks and their different aims and objectives and how they link together. Missing is a link between Friend and the core, which is the Africa-Europe Cluster of Research Excellence, because one of the key themes of the core is bringing together the hydrological expertise of the African partners with the machine learning expertise of the European partners, predominantly at University of Ljubljana in Slovenia and Radboud University in the Netherlands. And that's a key link to Friend. The Arua group under the directorship had a strong focus on increasing transdisciplinary capabilities across the Arua group, and we concluded a big project focused on that last year, which I'll mention. But under the new directorship, my directorship, what I really would like to do is pull out the hydrological work and better coordinate the hydrological work across the Arua network and beyond. So these are our core partners for Africa and Europe, but I think the point here to mention is that we are not limited to working only with these core partners who are mainly Arua members and Guild members. We are absolutely open and encouraged to collaborate outside of this network. It's just really to provide a focus area for the work. So just the top part of the slide is just looking at our focus area in the Southern African Friend. So we are very much focused on African model development. And this builds on the work of Dennis Hughes, who was at Rhodes University and developed a number of models. And we very much focused on increasing the capacity of model development in Africa as well as model use in Africa. Currently, our particular focus is on a water quality model called WQ-SAM and a sediment model called WQ-SED. Our Department of Water and Sanitation in South Africa has selected WQ-SAM to use to update the national wastewater discharge standards. So this is a model developed at Rhodes University. So one of the focus areas is combining the two models so that we can better simulate the links between certain water quality variables and sediment. Department of Water and Sanitation also would like us to improve the representation of heavy metals. This is still a question mark because data are a problem. And then finally, a focus on improving the representation of bacterial components in the model. Just to opportunities that are available at the moment for anyone. There are 42 6-month postdoctoral fellowships open and applications are open at this link. And we are also running a workshop on AI and water research with University of Ljubljana at the upcoming Arua Biennial Conference at Makerere in Uganda. And the link is there for that. So just quickly to talk about a large project that we concluded last year called Unlocking Resilient Benefits from African Water Resources. This was funded by UKRI and worked across the whole network. The 3 South African sites were established research sites, so they had received a small bit of funding as learning sites, and the remaining of the funding went to the 6 case studies in other countries. We had Nigeria looking at contaminated groundwater beneath Lagos, Uganda looking at pollution from the Kampala coastline into Lake Victoria, Rwanda looking at nature-based solutions to tackle land degradation, Senegal looking at water pollution in Lake Gez, Ethiopia again looking at land degradation and land restoration. And finally, Tanzania, who worked in the Great Ruaha River Basin looking at water contestation issues. And this is my opportunity to hand over to Augustina, who's the Deputy Coordinator for the Southern and Eastern African Group, focused on East Africa, of course. And just for her to highlight a little bit of work that they're doing in Tanzania linked to this project and other projects of theirs. So over to you, Augustina.
Thank you for giving the introduction. As introduced, I'm Augustina Alexander, and the Deputy Coordinator for Friends, but also I'm the Senior Lecturer in the University of Dar es Salaam. So basically what some of the activities that are going on in Tanzania, they are focusing on addressing the water resources challenges and basically focusing on the water availability. And this is due to different challenges that basically some are due to the changing climate, but some of them also are basically fired by the human activities that are going on. But so if you look at the Tanzania, you could see that we consider it to be abundant in terms of water. But when you look at it especially, there are some difference in availability of water based on the hydrological, climatic, and geology, but also significant in the seasonalities across the country, and also the issues of quantity and quality based on the geology. There's some part of the country that has geological occurring pollution. Next. I don't have control. Yes, so most of the activities are trying to address the water stress that is facing most of the basin. And if you look at the challenge and you look at this map, you could see that we consider most of the basin to be water sufficient, but you could see also some of the basin are already water stressed. But the most alarming condition, next, Jen, is the declining trend, which is showing the declining trend in terms of their per capita renewable water resources. So even the basin that seems to have to be abundant in terms of water, they are also this trend is very worrying that they might not stay the same over the years. Next. So it's even complicated when you look at the basin that has a very complex ecological system with a number of competing water users. The basin like Great Ruaha, that's the project that Jen was talking about. with irrigation, high demand for irrigation, hydropower, domestic, but also you have the national park, so the demand for environmental flow is also very high. So next. So in order to address that, we look at the best way where we can have a project that will look at the problem in a more wide and try to see how to address the challenge, looking at different aspects of the problem, because we have peoples of different understanding, different demand, different interests. We have the national interests, we have the regional interests, because the Great Rice refers the regional food basket. But also we have the national park, which has the other interests. So we look at the social aspect of it. We look at what does the science tell us in terms of water availability, the climate issue, and project that. And at the end, we were able to work on the water allocation model and try to see how we can improve the inefficient use of water in different areas. So this is one of the models that we came up with in trying to see how we can allocate the water resource in the basin, but also considering these different aspects, which is social, power influence, human behavior, the different development plans that are there. That's why I was talking about shifting priority that comes with the developments, but some of the management plans that are already in the basin. Next. So at the end, we had the adaptive management approach that considered the social aspects, where we engaged with the stakeholders to try to understand their needs and work with them through the process to make sure that we have that the participatory governance. But also we rely also on the science and work on the hydrology also and see how the human activities have impact the hydrological processes and the climate change, which affect the variability of water. And all these were the input to the management model, which was allocated water allocation model, and try to optimize and see how much water is available based on different climatic scenarios that are there. Next. Yeah. So at the end, probably what we ended up with, we were trying to see how we can meet we can work with unmet demand, because at the end of the day, what we were trying to compare is what the demand that is there and water availability based on different climate, different scenario, what will be the available water against the demand that is there in the basin for different activities, for different at different points of as where the input for the allocation model. So different allocation points, we are able to measure the demand versus the water availability and propose different measures on how we can work to meet the unmet demand under different climatic scenarios. Thank you, Jen.
Thanks so much, Augustina. Okay, so moving on to the seminar. Sorry, let me skip that. Yeah. So today's seminar is a small part of a larger project, which was led by David Gwapedza, titled "A Stakeholder-Driven Process to Develop a More Equitable and Sustainable Water Resource Management Plan." We worked in the Western Cape of South Africa in a semi-arid, water-scarce region, which is intensively farmed. Here you can see the two specific catchments we worked in. The limitation to agricultural expansion here is not arable land, it's water. And you can see in the right-hand image the numerous farm dams or small dams that have been put on the river or built on the river. These are predominantly owned by farmers or consortiums of farmers. One thing you don't see in this image is the extensive transfer networks that have been set up between farms by farmers. So farmers could be transporting water upstream, outside of the catchment, across the valley, etc., to either an adjacent farm of theirs or through some agreement with another farmer. This is highly protected information. You cannot access this information. Farmers protect it because this area is a very wealthy farming area. There's a lot of money that is made out of these farms, and there's a significant amount of lawsuits that happen over water between farms and farmers. So upstream farmers not releasing water downstream, transferring it away from the network. So farmers guard the information carefully. Thankfully, satellite imagery really helps us fill in a lot of the gaps, not all the gaps, but a lot of the gaps. But essentially, we came into this project to help the farmers to put together a water management plan and to work better and more collaboratively together to produce this water management plan, because the Department of Water and Sanitation has halted any new development until they've got one. So besides the hydrological modeling that we did, which we used SWOT Plus and the Pittman model for, this is a South African model, we developed 3 other models. One was an agent-based model, which looked at the impacts of different trajectories of change. So we looked at expansion of farmland, new dams, climate change, etc. And that was a farm level analysis, looking at the impact of these different changes on every farm. In blue is the water sharing model, which was the focus of Sinetemba's PhD, and that's going to be the focus of the seminar today. And that essentially looked at how do you distribute water in droughts or dry periods, which are very frequent in this area. So each farmer has an allocated water amount by Department of Water and Sanitation, but on those dry periods where there isn't enough to fulfill everyone's allocation, how do you share that water among very well-resourced farmers, less well-resourced farmers, communities, etc. And lastly, a water balance tool, which was designed for post the water management plan to assist the farmers in day-to-day operational compliance in terms of the allocated amount as well as in-stream flow requirements. If you're interested in the wider project, on the right is the final report, which a Google search should pull it up from the Water Research Commission website. On the left was a stakeholder product we developed, which was essentially explaining very simply the different tools we developed and how they can be used, why they're useful. And I'll put a link in the chat if anyone's interested in accessing that report. Okay, so I'm handing over to Sinetemba to give us a more detailed overview of his water sharing tool. Thanks, Sine.
I'm going to speak to you about a model we developed to try and help support decision-making when it comes to water reallocation at a local level. Next, please.
Sorry.
Yeah, you can go next. So, now I'll go one back.
Oh.
Yeah. So water scarcity is one of the new norms in Southern Africa, which and Asia, costing the region about 170 billion over the last decades, and about 80% of jobs at risk. If you've seen the recent statistics, you will realize that nearly 40% of youth in South Africa is currently unemployed, and that is tightly linked to water. So essentially, water security is important for prosperity and peace. In a way, water security we can think of as a tolerable level of risk within a society. So the key question then becomes, given the natural variability in water and the growing demand and all the other complications that Augustina mentioned recently, how do we share when there's not enough water to go around? Next, please. Next again. Again. Sure. So South Africa is arguably in a better position than many other countries in Southern Africa, in that we've got arguably one of the best water laws globally. And one of the key principles of our law is that it embraces or it emphasizes fairness, but the issue with the word fairness is that it focuses on the outcomes. So I'm going to speak here about equity instead of fairness because I'm trying to focus on justice. Because as Augustina was mentioning, when it comes to water, there's many interests and changing interests and many preferences which have to be also considered. There's different historical backgrounds, there's different cultural realities, and as Jane was talking just now, there's also power imbalances when it comes to participation. So we are also going to be talking about allocation as a form of reallocation, not the primary, but the secondary, which is in a way a renegotiated agreement on how water should be shared in times of difficulty or shortage. Our act says it's only the reserve that has right to water. So the reserve is basic human needs and ecological water requirements. Thereafter, water should be licensed, and the minister should also ensure that there is reallocation or a water allocation planning system to support reallocation in terms of shortage, growing demand, new demand, or changing demands. But this is not always the case because it is difficult to achieve, and at times the institutions are not well in place or well supported. And there's an important aspect to water reallocations, which is that when you move water from one user to another, someone loses and someone benefits. And both these losses and benefits need to be quantified. However, this is often left to the specialists to do. Next, please. And the actual people, next one, Jane. The actual people who are affected by these changes do not necessarily understand how these risks and impacts emanate. Next, please. Or they do not understand how to articulate them. So, knowing all of this, how then do we support decision-making at local levels towards equitable allocation or water sharing? Next, please. Jane already mentioned this. Just to reacquaint, the project is situated in a larger, so my model was tested in a larger project where many other models were being tested. And essentially, next please, my focus was understanding hydrology and demand and trying to determine possible ways to share water. We did have an objective to support the locals in developing a water management plan. But because, as I was saying, there's issues of power imbalances, next please, and power play, when the most powerful users refused to be part of the process, we had to adjust the objective of this particular model. And it was now shifted to demonstrating how equitable allocation decisions can be made possible to alleviate conflicts and social shortages and conflicts using uncertain data. I'm not going to be telling you today about how the co-creation and serious game was developed. I am not going to dwell much into the socioeconomic data that was collected. I'm just going to give a brief detail on how the model works and its schematics. Next, please. Otherwise, all of that information is available in my PhD thesis at Rhodes University. You can search it online, it will be available. To understand this, I used two concepts. It was equity, which is fairness or justice, and its four pillars: recognitions, contexts, procedures, and outcomes. And I coupled that with socio-hydrology, which is a dynamic evolutionary interaction between nature and society. And the picture on the right from El Shafi reminds us that socio-hydrology focuses on feedback loops between land use, water management, and community response. And the hypothesis then we're trying to respond to is, when there's water shortage, we can expect increased community sensitivity and a change in behaviors. How can we try to intervene there so that we try and at least maintain some form of social stability and prosperity? Through the social hydrology lens, we can be able to predict the changes in one part and how they can impact the entire system. Next, please. A key component of the work we're dealing with here is uncertainty, particularly hydrological uncertainty. And when we speak about hydrological uncertainty, there's four things in mind that we must keep. It's the quality of data that we have. It's the impact that data has on our ability to calibrate the models. It's the structure of the models, and it's the parameters that we use. Those four things interact, or they dominate one way or the other in terms of giving us the level or the confidence in stream flow estimates. Next, please. So why is it important to understand uncertainty in decision making? Well, Augustina was just mentioning about spatial and natural variability, spatially and temporally in Tanzania. It's the case here in South Africa as well. And one of the key limitations is that there's not enough point data or observation data. So we have to then incorporate uncertainty to understand the range of possibilities in terms of water availability, which without, when water is allocated, it's difficult to say what must happen to the surplus if there's more available, or who must sacrifice when there's less available. Next, please. One of the questions I was asked by my examiners was, how was fairness then relevant? Well, it's simple. If you want to adopt or to make more robust decisions in equitable allocations, you have to try to give water users or decision makers as much information as possible to make decisions, not one point, but a range of possibilities, and allow them to play with that. So that's where fairness is relevant. It's really in that decision support towards robust decision making. Next, please. Now we're moving to the model itself. I'm going to try and speak to the right, but you can always read to the left if I'm leaving you behind. The model is novel in various ways within the context of Southern Africa. First, as I spoke, it explicitly incorporates uncertainty, which is not a norm. So you can use historical uncertainty, or you can project with climate and use future uncertainty. And then you take the data and come up with natural water availability, in which you will generate 10,000 ensembles of possible natural runoff. And then another key component is socioeconomic data. Why is socioeconomic data important? Well, water users need to be involved in water allocation decisions in order for them to uptake the decisions. And the information we need from them is the actual water uses, which in this case, Jane did say you can always pull those up from remote sensing. Storages, we also need to understand their allocation preferences or priorities. That one, you need to engage the community and try to understand who must be prioritized for supply when there's times for shortage. And then you need to come up with user risk profiles, essentially trying to bring together the potential impacts and potential coping capabilities when it comes to water shortages, not only winter seasons, but also drought spells. And then, as I said before, the water law in South Africa is clear. The reserve has the right to water, and therefore a water allocation model that is acceptable has to incorporate e-flows. This model incorporates e-flows as they are computed in South Africa. And then what happens is, once you've taken all this input information and thrown it into the model will look for either, if you have enough computing capabilities, you can take the 10,000 ensembles or choose a sample which will be random. If you have a dam in which you are pulling your water from and not from runoff river, it calculates the water balance. And from that water balance, it estimates the remaining water availability. If for the water users that you have, which in this case or in this model, it groups them into any five categories. So it could be industry, agriculture, domestic, or urban and rural, anyhow you want to configure them. It asks the question, is the demand met? If it's not, it takes the shortages and throws them and searches from the 10,000 ensembles that for each ensemble, how frequently would each user be in shortage? And it plots those on the one side. And then it uses a Gaussian transformation to change the deficits into impacts. I can't explain this theoretically. I would have to show you in order to understand, or need slightly more time. So you'll have to take my word for this one. It translates the deficits into impacts, and then it takes those impacts and prompts the user now to select and start planning for water allocation. Why are the impacts important? Well, remember, we're not confident about the amount of water that we have. So another key novelty of the model is that it forces decision makers to think about the consequence instead of the actual deficit, because at least the consequence is something they are more familiar with than the deficit. And hopefully using that, they can better plan and come up with a robust or much more acceptable decision in the long term. Next one, please. I'm going to spend some time trying to explain the novel allocation scenarios that we have. So essentially, the normal one is what you have here under proportional I don't have a pointer, Jane. I don't know if you can point. If you can see proportional sharing, that's the one that is much more common. Essentially, proportional allocation, you take the water that is normal, that you normally have, and for that reduced supply, you cut similarly across users. What this strategy does inevitably is it prioritizes larger users who often play an important role in the economy. So then if the community values economic growth, employment targets, this is the strategy that is typically used. However, not all communities prioritize economic growth and employment. The other option users can explore with is pizza slices. So what pizza slices is, it says for the available amount, keep withdrawing until the supply run out or until all users are met. The consequence of this strategy is that the lower level users are protected in the assumption that they suffer a lot more from small cuts of supply. So think about a rural community versus a commercial farmer. A commercial farmer can survive a 30% cut, but a rural community may suffer substantially from a 30% shortage. Another one is proportional sharing with community priorities. What this one does is it takes pizza slices, proportional sharing, and it adds the priorities that were set by the community. This way, users who have been deemed by the community in terms of users who have been deemed by the community as important, plus the economically important users can be prioritized in some form or some way. And the last one, which we proposed, was share the pain. Share the pain works like taxes in a way. So what it does is all user groups will experience the same level of impact when water is cut. And it doesn't cut based on shortage. It searches for a part where all of us will suffer similarly to recover from the shortage. When we demonstrated this with the farmers, they came up with another strategy, which we did not see coming. One day I'll write about that one, and someday I'll get to tell you about it. But let's move on, Jane. Next one, please. Thank you. Earlier on, I spoke about the model's ability to translate deficits into impacts. And essentially, for the 10,000 ensembles, the model asks each user, how frequently will you be in shortage? And it arranges those deficits from 0 to 100 in a flow duration curve. Sorry, in a distribution, frequency distribution. Then it translates them and does the same for impacts. Then essentially you'll have low impacts in 0 to 1, 0 to 10. So progressive impacts from 0 to 100, moving from low to high. And this allows us to search and apply the strategies. I will show you examples of that just now. Please, Jane, press. Let us take, for example, if we were doing the normal way of sharing of distributing water, which is you cut water equally across all users. What you now see in front of us is the environment would not be cut under this strategy because it is naturally curtailed unless you are treating it as a user, which in some countries that would be the case. So let us ignore the EWR for once. You see that user one, which in this case was a commercial farmer, they suffer less impacts, only 50% impact compared to user three, which was a downstream under-resourced farmer who would face over 90% impacts. Now, for us scientists, this is where we leave it. We leave it at analysis. The beneficiaries or the water users themselves or the decision makers must come and say whether or not this is a fair allocation strategy. If they accept it, you leave it and write their water allocation plan. If not, you move on to the next one. Let us take a second one now, Jane. In this case, we're now exploring share the pain. Share the pain. In share the pain, you arrive at 30% of impact. And now most of the impacts are transferred to user one, who is more resourced. Because of their resources and the arrangements they have in place, they can better be able to, we assume in this particular case, they are better prepared to buffer the impacts. So in some cases, they would accept this strategy. In other cases, they would not. Once again, this is where it becomes important to have all the representatives, or at least all the beneficiaries represented in the water allocation decision making. And this is why it is important to give them the impacts instead of the volumes, because with impacts, you get them to think about consequence instead of the actual volume, which sometimes is in secret. They don't like sharing their actual water uses. Next one, please. I'm going to briefly now run down how we collected the socioeconomic data to input into the model. Next one, Jane. Those are some of the decision makers you saw in the background. So in the KBV, we had 3 or 4 water users: the reserve, which has the right to the environment, farmers, and non-farming residents. And what we needed from them was priorities. Who needs to be prioritized when there's not enough water? And for that, I used a multi-criteria decision-making, and I drove all around the farmers, trying to get each one of them to contribute into the prioritization. Why did I go to them individually? Well, in fairness, when dealing with marginalized communities who are not familiar with engaging and where there's power dynamics, one of the responsibilities of us scientists is to train these marginalized communities and better prepare them for participation in these decision-making environments. That's why I had to go to them individually, so as to get them as much representative answers without the influence of their counterparts. The second part, or the second piece of data you need, is socioeconomic impacts, which both these are collected flexibly. But essentially what you need for socioeconomic impacts is it has to be holistic enough to give you the vulnerability and the coping capabilities. So for example, in this case, we know that if you have water storage facilities, you are better suited to buffer drought impacts compared to someone who doesn't. Next one, Jane. The socioeconomic data is indispensable because it allows us to force the model and give us impacts that are site-specific. If you look at the landing screen of this model, you may not necessarily see where the socioeconomic data comes in, but you've got impact index up there. So when you take your socioeconomic data, it must be in percentages, then your weights must also be in percentages, and then everything else will be automatically calibrated or recalculated from your other input tables. Let's go, Jane. Then you go plot curves. Let's go, Jane. Let's see if we can plot our curves. When setting up the model, you choose if you want to set it up at quaternary scale or sub-quaternary scale. In this case, we chose sub-quaternary scale and grouped our farmers according to their categories or what they farm. As you can see in the different sub-basins, we've got different farmers falling into one category, not necessarily because they are owned by the same person, but because they share similar characteristics. The input water use was mainly, so the model was run from 1994 to 2021. We used a Pitman model, which James spoke about, and the ecological model or the eFlow model, which she did not mention, but it was also part of the suite that Rhodes University hosts, multi-criteria analysis for priorities, and the user risk profiles. And then for irrigation demands, we base them on historically available data because the farmers would not give us that data. But it should be data that's available if they are willing to give it to you in reality or in a different setting. Next. This is how e-flows come out in the context of South Africa. They come as a flow duration curve, and this is how you take them into the model. I won't go into detail about how they are computed, but the part I'm trying to come to here is that the model looks for an ideal e-flow, wants you to input the ideal e-flow level and the level at which the water users are able to achieve e-flow requirements. And both of those will be important when it's time to compute the impacts faced by the environment, because it's not only the socioeconomic users whose impacts must be considered, but also those of the environment. Next, please. These were the e-flows for the different sub-basins, which were downscaled using the natural, the ones available at a primary catchment scale. Next, please. This is one of the first outcomes of the model. This is the landing screen. The model gives you first the long-term impacts arranged on a 0 to 10, 1 to 10 grouping, which is the impact grouping. So 1 represents low impacts and 10 represents high impacts. As you can see, for example, users 2 and users 3 did have some high impacts. This is where you decide if you want to continue exploring a scenario or you want to leave it. If you see some high impacts, then you are propelled to move in and investigate why that is. Next, please. And then remember I said if there's a dam storage, the model will start looking at the dam performance and then later compute the deficits for each user. What you see here is that it seems in the basin, there's more than enough water for all those who have dams. But we have to remember it's not everyone who abstracts water from the dam, and dams are normally upstream in this catchment because of historical arrangements. And one of the users' key requests was for us to see a scenario if they can build a dam, but we could not do that in this particular case because there were users who were not there. So we are not able to move forward unless we have got as much information as we needed. But one of the key challenges of this particular outcome is that it's difficult to communicate the outputs to decision makers. So we need to be slightly creative in how we do that. This is how the model gives it to you. So this is how the model gives it to you, but us as modelers, we have to find a way to translate these further for a level that users can play with and grab with. Next, please. The same thing here. This is the long-term frequency distribution for all the calendar months. And what you see here for the different strategies is that different users slightly experience different impacts. For example, to the left, you've got users upstream, and to the right, you've got users downstream. And you can see that users upstream and users downstream did have some high impacts, but the high impacts are not the same. If you take, for example, user 1 and user 2 upstream, they have up to 16 months of impacts under share the pain. But under the currently used strategy, which is B, split the bill, user 1 would have only up to 7 months compared to user 2 who would have to up to 16 months. User 1, in this case, was farming mainly crops such as onions, cash crops such as onions, and user 2 was planting crops such as orchards, apples, deciduous fruit, and citrus. So the question we had then for the farmers is it fair for the deciduous fruit farmer to have shortages? They would have different responses. For example, we found out that they sometimes they have ways of adapting to their deciduous fruit. So they would prioritize important crops or move away from less high value crops until water is plentiful. Nevertheless, we now were able to show them that it's possible to take a different approach into sharing so that you don't have to do that at all. But there has to be an agreement from all users, which in this case, user 1 was not always attending. Next, please. So now I take all of that information I showed you behind and you arrange it into this table, which will be used by water users for decision making. And essentially what you have here is the number of months from low impacts, number of months from medium impacts, and number of months from high impacts. And we see now that for the user 2, which I was speaking about just now, they would have 11 to 18 months of high impacts over 30 years. We don't know when those impacts will occur, but I can drill into the model and figure those out. And we found that actually these impacts occurred during the dry months and they were worse during the drought years. The question is, would their upstream counterparts be willing to play or to at least release some water to them or to change a strategy? That remains to be explored, but this is the kind of information that they would essentially find most valuable in decision making. And this is why we needed the impacts, i.e. the consequence, instead of the actual deficits. And one of the things we struggled with was we had to be conservative in our uncertainty estimates in our natural stream flow estimation because the farmers asked for it to be that way. In reality, the uncertainty would be much higher. For example, the impacts could be 11 to 23 months if the uncertainty was as we wanted it to be. But in this case, we had to respect the wishes of the farmers who are not familiar with playing with uncertain data. Next, please. I think this is the conclusion slide now coming. Next, no, we're not going to speak about the game, so we'll leave it. We did produce a game to communicate all these outcomes. So in closing, the model was able to show the importance of e-flow requirements, which are often not respected by farmers. It was also able to show that there's a positive impact, or there are impacts coming from upstream developments, and these can have an effect on downstream communities or water users. Communicating the model outputs to all the farmers was particularly challenging. We kept on trying to find different strategies, but if you consider language, technical difficulties, it was not always easy, but we kept on trying. Farmers were able to see the importance of uncertainty in decision-making, even though it's currently not embraced in decision-making at a national level or even within Southern Africa. The tools, once again, does not show deficits. It shows consequences of shortages as impact. And one of the resource managers that was there, who was protecting Split the Bill, tried to bash the model as much as they could. And we were able to see from them that actually most of the issue in trying to find robust decision does not lie only with water users. It also lies with people who are in charge of administering the decision. So in conclusion, there's a need to roll out the model across different scales, which we are still in the process of trying to secure funding for that, but we are not always winning. But hopefully we'll get better there, or we'll get some positive answers sometime soon. Next time. That's the team. So one of the key take-home messages is that this type of work is not possible without good collaboration across multiple stakeholders, without collaborating with local water users. And co-creation is definitely not a simple thing. Communication becomes an issue, trust becomes an issue. And one of the key prerequisites is that researchers must immediately state their interests upfront when going into these spaces, especially in a place like this one where it is not normal that outsiders are let in. Thank you very much for listening, and I don't know if I have time for questions.